So we are going to try lesson 34, part 2 again. I did this lecture earlier and it just started to go so bad. And then I tried it again and it went even worse. And so now I've gone outside and taken a break. And so if you are struggling, I want you to go outside and take a break because it has helped me a little bit. I guess we'll see. And so we're going to talk about nuclear stability. So the video before this, we talked about what nuclear particles we're going to be looking for. We balanced nuclear reactions, and now we're going to talk about stability. So when we're talking about stability of an element or an isotope, we're being specific about how stability refers to, and that's how likely a nucleus is going to be to disintegrate. So for the most part, it's taking something heavy and breaking it into something lighter. Probably multiple something lighters, not just one lighter thing, but multiple, because we have to have the conservation of mass. So this and the rest of this says, and give off elementary particles. So we know that it's probably going to be something lighter plus one of the 5 particles or the gamma ray that we talked about earlier. The stability is determined by the ratio of attraction to repulsion within the nucleus. So we're only talking about nucleons. Okay, so we're not talking about electrons. And so when we think about repulsion, we're talking about the proton repulsion because they're like charges. They don't really want to be near each other. So crowding them all in a nucleus is not a great way to stabilize an atom. But what we do is we have this attraction between neutrons, which helps to bind and create this strong nuclear energy to help hold the atom together despite the fact that the proton-proton repulsion is happening. So we're going to only focus on nucleons, and so we're looking at neutron to proton ratio, which is N over P, and this is number of neutrons divided by protons. Now, we have a couple of rules that we're going to use to predict stability, and there are 4. And so you need to know the rules, and then we're going to talk about reading the chart, which I'm going to do a better job about it this time. So nuclei that contain the following number of protons or neutrons are going to be more stable than others. And so these magic numbers are called 2, 8, 20, 50, 82, and 126. Okay, so they're just the magic numbers, and you do need to know what the magic numbers are. Now, I had an unfair advantage that 2 and 8, well, that's my birthday, February 8th. And so I could always remember those 2, but then I struggled with 20, 50, 82, and 126. There's really no specific relationship between the numbers themselves, if that makes sense, but there's a reason why those particular numbers are stable. But there's no like add 6, add 12, add 30. There's somehow you just need to know them. Now, for example, helium, which is also an alpha particle, has 2 protons and 2 neutrons. So helium actually has 2 magic numbers, and when that's the case, we call this double magic. They are going to be particularly stable, not just kind of stable, but super stable. Now, the second rule is going to be nuclei that have an even number. So you look back at our magic numbers, they're all even numbers. If they have an even number of both protons and neutrons, they're generally more stable than those with odd numbers. So helium, double magic, super stable. If we take something like fluorine, I'm also going to write it the right way this time. I wrote it as Florida earlier. This is going to have 9 protons, and this particular isotope will have 10 neutrons. So it does have a positive number, an even number of neutrons. It's also positive, an even number of neutrons, but it has an odd number of protons, so it's not as stable as something like fluorine 18. Okay, fluorine 18, oh, that's wrong. No, something as stable as helium. Oh, it's not. We're not starting off good. Or carbon 12. Carbon 12 has 6 protons, 6 neutrons. When we look at carbon 13, on the other hand, carbon 13 has 7 neutrons, which means it's less stable than carbon-12, which is what makes carbon, or part of what makes carbon-13 a great isotope to monitor for half-life, because it is unstable and it is going to decay into something more stable. Okay, so that's the second rule. The third rule is that all isotopes with the atomic numbers higher than 83 are radioactive. So guaranteed, anything higher than 83 is radioactive. But there are some exceptions to the ones that are less than 83, and that's technetium, which is used in imaging, and promethium. But I don't really know of a use of promethium, to be honest, but both of those are radioactive and they're less than atomic number 83. Okay, so elements number 1 through 82 are not guaranteed to be radioactive. Everything over 83 is absolutely radioactive. Now, element number 83 is bismuth, so which is also used for imaging. There's a bismuth drink, and you drink it, and they do imaging of your stomach, intestines, and things like that to look for blockages, abnormalities, anything like that that can't be very quickly seen without something like an endoscopy or colonoscopy. So bismuth and up. Now, one of the things that's important to know is that lead is the last most stable element. And so what we're going to see is in our radioactive decay series, when things are breaking apart from something heavy to light, something lighter, they're usually all going to end when they get to lead. So like uranium is going to decompose and eventually form lead. Plutonium is going to decompose and eventually form lead. So that's something that they tend to have in common, which, lead is something that's very toxic. It's very hard to get rid of. It's poisonous. It's just not a great thing, but it's a great use for building, but it's poisonous. And so it's kind of strange that one of the unique properties about lead is it's the last most stable element. All right, but this graph right here is going to be the belt of stability. Now the red line right here is where the neutron to proton ratio is equal to 1, meaning for every neutron I have a proton, and so on and so forth. So we know that that's true for elements like carbon. Carbon has 6 protons and 6 neutrons. It has a 1-to-1 ratio. But same thing for helium. Okay, for every 1 proton, it has 1 neutron with a total of 4 total. And so we can see that for a little bit here, maybe till we get to, it's kind of hard to gauge. This is a little bit higher than 20. But for elements that have an atomic number maybe greater than 22, that 1-to-1 ratio is not a good ratio to have, because what we're aiming for is within this red area, because everything in this red area is going to be stable. Okay, so as the elements get heavier and the atomic number gets larger, the 1-to-1 ratio is not the right ratio to overcome the proton-proton repulsion. So what we have to do is we have to start adding more neutrons for every 1 proton. Okay, and so what this means is that eventually we're adding significantly more neutrons for every 1 proton that we're adding, so that the atom can be stable. Okay, now we have 2 regions on this graph, and I shouldn't have used my yellow. Maybe I'll erase the yellow because that shows up really nice on the graph. All right, so we have this region here, the area above the belt of stability, and then we have the region below, which is below the belt of stability. Okay, now we can use the belt of stability and the location of the atoms on the graph here to predict whether or not it's stable. So you're going to see that carbon-12 is probably, because this is number of neutrons versus number of protons. So carbon-12 is going to be over here somewhere 6-to-6. Helium, 2-to-2. So we see that these lie on the belt of stability. And so we would predict them to be stable. Now, if something is up here in this yellow region, we know that it's going to be unstable. Therefore, it's going to want to decay in a predictable way that moves it back towards the belt of stability. And that's going to occur through what's called beta particle emission. And so basically, it's releasing an electron. Anderson, stop hollering at me. I'm back here recording a lecture. I have created a monster. What? If you can have my water. Okay. If it's in the blue area, it's also going to be unstable, and it's going to want to change something about its atomic makeup to shift it up to the band of stability. And it's not as simple as saying gain a proton, gain an electron, or gain a neutron. So I want to remind you that we're not talking about adding protons and neutrons to the nucleus. We're talking about a particle of some sort being lost or being gained that's not a proton and not a neutron, because it's not as simple as to go in and physically add something into a nucleus. It needs to break apart, but into something smaller, but not necessarily, we're not talking about like adding with tweezers, like tiny atomic tweezers, a neutron and a proton, okay? All right, so if it's in the blue area and it's unstable, meaning its ratio of protons to neutrons is not correct, so it would probably be closer to a 1-to-1 ratio, so it's too low. There's two options here. The first option is that it's going to undergo what's called positron emission. So you have to remember that positron emission, it was the positive electron. So it's going to release a positive electron. Okay, so I'm going to write an electron with a positive charge. Don't make a habit of it for anything else except for nuclear chemistry. The second option is that it's going to undergo what's called electron capture. I know that's going to erase all my blue. Okay, electron capture. And this means it's going to essentially gain an electron. Okay, two options. All right, so let's look at predicting. And one of the things that I wanted to do is to give y'all an opportunity to read this graph. So I'm going to look up examples that say predict where this particular atom is going to be above or below and what process it's going to undergo, because that's a great multiple choice question that I've seen on the ACS exams before. Granted, I have not seen your current ACS exam, but I just don't have any written in the notes. So I'm going to provide some examples for y'all to look at after you're done with this lecture, and then post answers so that you can make sure you're interpreting the graph correctly. All right, so predicting reaction types. So the nuclei, we said they want to be stable, so they're going to undergo reactions in order to become more stable. It's the same thing as when we talked about endothermic and exothermic reactions, when we said, well, the desired product or reactant is going to be based on the energy levels. For an endothermic reaction, the reactants are lower in energy, therefore preferred, and then an exothermic, the products are lower in energy and therefore they are preferred. And so that's what we're looking for. We're looking for that lowest level of energy to be the most stable. Now in this case, we're not looking at hills per se, we're looking at where they are compared to the belt of stability. That red area in the graph above that allows us to predict whether it's beta emission, electron capture, or positron emission. So if it is above, we said that this is going to undergo beta particle emission. They have a neutron-proton ratio that is too high. So we're going to say it's higher, much higher than 1. Okay, too many neutrons for every proton. So they're going to want to lower that down, not to 1-to-1, but maybe like 1.5 to 1, maybe it's 2 to 1. And so this is what it would look like. So if we have carbon 14, this is going to have 6 neutrons, 6 protons, 8 neutrons, which is ironic because 8 is a magic number. Okay, but its neutron-proton ratio, if we think about 8 divided by 6, that's definitely not 1 to 1, right? Because we know that 6 divided by 6 is 1 to 1. In fact, this is going to be a 1 to 0.33 to 1 ratio. So that's too high. Now, when carbon-14 undergoes beta particle emission, it's the same thing as losing an electron. It's going to form nitrogen-14. Okay, so that's the isotope of nitrogen. And if we think about what nitrogen is, nitrogen has 7 neutrons, 7 protons. Well, lo and behold, now we have a 1 to 1 ratio, which for those smaller elements, that 1 to 1 ratio is what's preferred. Anything less than 20 is going to prefer, or 22 is going to prefer that 1 to 1 ratio. So we can see here that it moved it down, that ratio, into a lower number, which is what we needed. Okay, now positron emission, this is one of the options when the ratio is below the belt of stability. The other one is electron capture. Okay, so it's below. They can either emit a positron, which is the same as a positive electron. And so if we look at this, we have potassium. I almost forgot what potassium was. Whew. We have 38 divided by 19. Oh, sorry. It has 19 protons, 19 neutrons. So oddly enough, it isn't a 1 to 1 ratio. However, these are getting to be those heavier elements, which we said that over here we can't quite say for sure that this is the right ratio, 19 to 19. It might be just barely below the belt of stability. Now, when potassium undergoes positron emission, the atomic number is going to drop down, but the mass is going to stay the same. So the number of neutrons is not changing. What's changing is the atomic number. So in this case, we go from a 19 to 19 ratio, and argon is going to have, not make a liar out of me, 20 neutrons and 19 protons, and the ratio there is just barely over 1 to 1. Okay, so it may not be the most obvious example of what would be below the belt because it is close, and 1.1 and 1.05 are really not that different. However, if it's below, you will clearly know in the examples I'm going to give you that it would undergo positron emission. The next one is electron capture. So it's gaining the electron. So we have the example of argon 37. So we have 18 protons, and we're going to have 19 neutrons. Gotta make sure I do that math correctly. So the ratio here, it's too low, which again, if we think about the position of potassium and argon, they are fairly close to each other. They'd be in the same-ish area as the within the belt of stability. Now, it's going to form chlorine. The mass number remains unchanged. The atomic number is going to go down. And so then we end up with a ratio of 20 divided by 17, which gives us a higher value of 1.18 to 1. So it would go up into the band of stability. Okay? So that's just showing you how the ratio changes. Okay. So let me insert some spaces here. All right. So this says the boron isotope 13. So this is boron 13. And just to remind y'all, sometimes the little number doesn't show up here because the atomic number doesn't change. So there's no reason to really specify it per se. And so the only number you have to be given is the mass number because it doesn't always match what's on the periodic table. Okay, so boron is atomic number 5. So if we think about what this means, this is going to have 5 protons and 8 neutrons. And so that ratio, no, we didn't do that one earlier, is actually going to be higher than the first example we did, because it's going to be 1.6 to 1. Okay, so that's the ratio of neutrons to protons, which is actually much higher than the first example we did, and it's definitely up here in this area above the band of stability where 1 to 1 is what we really need. And so because it's above the band of stability, I'm going to predict that it's going to undergo beta emission. Okay, and so what that's going to look like is boron is going to emit the beta particle. You could also write it as an electron. That's not incorrect. The mass is going to stay the same. The atomic number is going to go up. Element number 6 is carbon. And based on the example we did before, we know that carbon-13 has 7 neutrons. Divide that by our number of protons, and we get a ratio of about 1.17 to 1. I don't know why I made that 11. Okay, so it lowered it down, which is what we need for it to do to come back into that band of stability. Okay, so hopefully that is definitely the better version I gave of that today for the third time. And so now take a break. We'll come back and do the last part of lesson 24, which is nuclear binding energy, which is going to have a little bit of math.